My name is Andrew Moore, and I'm going to show you a little program I wrote in the Go language using Faiface's Pixel 2D animation library. Right, and this is all about something which I regard as incredibly beautiful, and I hope to convince you as beautiful. It's something called a Voronoi diagram. And this, my friend on the screen, is not a Voronoi diagram, it is a dot. We're going to add another dot. 2 dots! And I need to explain to you what a Voronoi diagram is. To do that, I'm going to color my dots. Now, first thing we have to understand about the dots in a Voronoi diagram is that they are acquisitive. They want territory. And so that they don't keep fighting over each other, we've got some simple rules. If you're a dot, the territory you own is the whole set of points in space which are closer to you than to anyone else. So, for this red dot, this is the set of territory it owns. These are all the points on the 2D plane which are closer to the red dot than the blue dot. And you're not going to be surprised to see what the blue dot owns. That's all very nice. Now, what we can do is notice that if these dots happen to be moving around, that of course the boundary between them is going to change. What they own is going to be different. Watching that boundary move is kind of hypnotic. It's nice to see it, and right now you see it looks pretty stable. When they go close to each other, whoop, you see it turn around like that. That's very fun. Now, in particular, with particular interest, is the boundary between the two regions. There it is, drawn nicely in black. And that boundary is the world's simplest Voronoi diagram. Voronoi diagram for 2 points is just the infinitely long line which separates them in the middle. Now, the big question, what the heck happens when we add a third point? Ta-da! As you may expect, you end up with something like this. The green point has come along, it's actually sneakily managed to gain the majority of all the territory on the screen. And sort of pushed back the blue and the red. And as we watch those folks play around, roll around, you once again see a pretty nice effect of the behavior of a Voronoi diagram with animated points. Isn't that rather aesthetically pleasing? I think so. What you can do after that, of course, is just start adding more points. So let's go a little bit nuts. There they are. Plenty of points wandering around, and just to make some more room for them, I'm going to make the dots smaller and the walls thinner. So this is what we in the business like to call a Voronoi diagram. The actual Voronoi diagram piece are the black boundaries you see. So next what we'll do is I'm going to show you how I prefer to view a Voronoi diagram. This to me is the perfect depiction of a Voronoi diagram. Get rid of those colors. Let's just focus on the incredible beauty and strange complexity that arises from when you draw these paths, which are the midpoints between nearest neighbor cells out of a set of points. There you have a beautiful Voronoi diagram. I think it's super aesthetic. I'm going to add a few more points and maybe slow it down a little, because it is something to gawp at and gaze at. Now, this is the kind of, to my mind, this is mathematics being an artist. I really approve of what mathematics has done here for us. Now, you could say that maybe it's nicer colored. There we have our colored version. It is kind of nice if we take away the dots and maybe thicken up the lines a bit. I think you'll agree that's also an aesthetic thing, though I prefer the raw plain Voronoi diagram. Let's see what it's like with more. Yeah, it's kind of like, you know, funky stained glass windows or something. Let's get back to Boringsville and the nice plain dots and lines that we're used to. Here we have a Voronoi diagram wandering around. Now, let's talk about some other interesting things about Voronoi diagrams. First one is what they bring to mind, what they remind you of. And for some people, let me pause it, looking at that, if you think of skin cells or maybe just the designs or patterns you see on some biological organisms. And it kind of makes sense because if skin cells were to grow by having a bunch of random starting points and they all just grew and grew and grew until they were pushing into their neighbors, this is the shape you'd see. I see other things when I play with Voronoi diagrams, as I do almost daily. And let's take a look at some of those other things. To look at this, I'm going to grow our number of points again quite a lot. As you see the number of points in a Voronoi diagram increase, when I look at this, it reminds me of what I see from an aircraft flying over England, my home country. This is not unlike the sort of shapes you see in the fields and the ancient walls between the fields. And that's also not completely crazy because it would be modeled well if we said that the English countryside was created by people randomly throwing down farmhouses. And then there was a rule that, yeah, you could farm everywhere you liked as long as it was closer to your farmhouse than anyone else's. Let's now get even more significant with the size of our Voronoi diagram. Add in a few more points, and as you see, I've kind of hidden away the dots again. And for me, as you start to go into these really detailed Voronoi diagrams, the thing it brings to mind is like someone has just thrown a rock at my computer screen. It's a very nice little sort of image of what shattering looks like. This one I can't really explain why it strikes me that way, or what a reasonable theory would be as to why it would end up looking Voronoi-y. But there you go. So now I'm going to bring down the number of regions and show you something else as to why I believe people, or at least I, enjoy so much seeing the animation of a Voronoi diagram. It's a peaceful, happy sort of sight. And part of the reason I think it is it's a sort of secure kind of thing. And if you watch very carefully each individual dot, what happens to it as it's running around. Let's take a look at one. That red dot there. You see that as the dot moves, it's just moving in a simple straight line where it bounces against the edges. But it's constantly protected by its own little piece of personal space, which is its own Voronoi cell. And that's why this is, to my mind, a much more beautiful image than simply if we'd had a bunch of lines joined together wandering around past each other. So now I'm going to introduce you to a friend of the Voronoi diagram. And to do this, let's quickly get back to where we started from, pause it, and let's get rid of a few of the points because I want to make this one pretty clear. A friend of the Voronoi diagram is an object called a Delaney triangulation. What it is you take each one of your points and you connect them with a pink line to any other point that is adjacent to the Voronoi cell. So if we look over here, for instance, this point and this point share this border, and so we've drawn a pink line between them. And this thing makes what is called a triangulation. Let me get rid of the Voronoi boundaries so you can see just the triangulation. And I'll thicken it up a bit because it's more aesthetic, I think. This Delaney triangulation is a special one. It is in some sense the optimal triangulation. It's the one which gives you the least misshapen triangles. And if you take out a pen and paper and try to make a triangulation by yourself of a set of dots, you actually will find yourself making an uglier triangulation than this awesome Delaney triangulation. So there. Just for laughs, let's see what bigger Delaney triangulations look like. I love them, but I don't love them as much as I like Voronoi diagrams. Voronoi diagrams, in my mind, are much more beautiful. So let's bring them back. Farewell, Delaney. All right, couple more Voronoi diagram tricks and then we're done. First thing I'm going to show you is what would happen if these were owned by farmers and they were greedy farmers. So let's do a quick examination of that question. I'm going to get rid of almost all the points, and I'm going to put one point here in the top left-hand corner. You see it sitting up there happily? Get rid of this one. Now, suppose this was the world as it started, and there was only one farm right over here, and then a second farmer came along and wanted to be as antisocial as possible, as far away from his or her neighbors as they could be. Where would they go? The answer, of course, is over here in the furthest corner. What I'm now going to do is actually add a new point where that antisocial neighbor has arrived. And we can ask the question, so if a third antisocial farmer came along, where would they live? And the answer is this, which happens, you'll notice, to lie on the Voronoi boundary, is the third furthest place to go. It actually ends up being equidistant from the two original ones. So put that one in. Fourth one ends up coming down here. And fifth one, the furthest place they can go here. And of course, as each new farmer gets added, they're not quite as far away from each other as they used to be in the old days, but still the process can continue and you'll actually see something nice emerging. Look at that. After we've had, what is it, about 10, we end up with a nice hexagonal thing. These farmers are end up being pretty hexagonal if they're all trying to stay apart from each other. Let's just add a few more of farmers, antisocial farmers, and most pleasingly, it doesn't take long before we see that they've formed another round of hexagons. If another farmer has to come in, then they're going to have to be a little closer, I'm afraid, and you'll see where this one's chosen to set up. But if we watch these farmers arrive, boom, 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 once again you see the emergence of a deck of hexagons. Isn't that a cute thing? All right, so I'll let them just move around now as they wish, while I tell you what we're going to do next. Next, I'm going to show you how, if your dots are arranged in particularly interesting ways, the Voronoi diagram does have some particularly interesting properties. So to begin that, let's get a kiln. Once again, getting rid of all but one point, who I will pause. And now, I'm actually going to do a whole series of new points along the left-hand edge. Get rid of that one in the middle. And you see what the Voronoi diagram looks like as we bring in these new points on the left. It's mostly kind of a set of parallelish lines and parallel stripes. Some of the left-hand points are trapped in little tiny cells, but others of them are lucky enough to have their cells going out way to the left. So here's a Voronoi diagram of a kind of a messy vertical line, and you see it's kind of funky. The reason I'm showing it to you is asking you the question, what do you think will happen if we add a new point around here? What would happen then to the Voronoi diagram? You decided? Well, I'm going to click. Bingo! This new point is delighted. It's gained a huge amount of space. I wonder what the shape is of this curve. It may look like it's part of a circle, but it isn't. And I'll explain why. I've removed it, and now I'm going to add the new point much closer to the line, like here. And you see this beautiful shape here. It is a parabola, and it turns out it should be a parabola, and it's based on some of the mathematical properties of a parabola, which I will not go into right now. Still, I find that a very beautiful thing to see. Final example of a fun thing to do with a Voronoi diagram. We are going to, once again, remove lots of points, and we're going to put a few points in the center. Let's remove this point up here, and we will have thinner lines for this example, for this demonstration. So as I put a whole pile of points in the center, you see one of the things that you get from a Voronoi diagram with lots of space around it. These rays of some of the points near the edge are lucky enough to have infinitely large cells that they own. So that's fun. Now, these Voronoi diagrams, these points, when I start animating them, they begin moving in a straight line with a random velocity, but they're all the same speed, just random directions. So the question for you is, what's going to happen to these points when we start animating them? Think about it, and let's take a look. It's rather nice. It's like a little explosion. They all come out, and now you see a little donut of dots moving out, and you see what that donut does to the Voronoi diagram. It's just growing like a sort of crystal or something. And the big space, empty space in the middle, is where the Voronoi regions of some of the outside dots get to exist. And now you see the dots at the top and bottom are bouncing off the walls, and they're wandering in towards each other, making this lovely horizontal Voronoi line in the center, which will eventually get disrupted, I believe, when the two sets of points finally meet up. Here they are, here they are, here they are, and speed them up a bit, and there we go. And that, my friends, let's give you a little bit more speed. That's a fast-moving and very happy and satisfying Voronoi diagram with which I, Andrew Moore, will say farewell.